This is the unit on tests of k-means, dependent samples. K is any number greater than 2, generally speaking. And when we have dependent samples with more than 2 conditions, 3, 4, 5, 6, we're going to opt for hopefully an Anova when we meet the assumptions. Here are the various terms that we're going to be computing. Sum of squares total, sum of squares between, blocks, and error. Now I've gone ahead and entered in the data for the first example in the workbook. What we have here are triplets who receive either neutral, positive, or negative questioning, and we're going to measure heart rate. So we're looking at the effects of emotionally provocative words or questioning on heart rate. Now these are triplets, so these scores are related systematically. That's why we call them dependent samples. That's why we treat them as dependent samples. Here are the terms. Here are the statistics we're going to compute: total, blocks, between, and error. And you can see that we're going to need to compute a number of different values here and a number of different intermediate terms. What I have also here are some second formula that are algebraically identical to the first, but these formulae are much easier to compute. So for example, we'll be computing the mean of the ith group, we're going to be computing the grand mean, we're going to be summing the blocks squared, we're going to be taking the mean of the jth block, and so on. Some of these formulae are very difficult to work with, so we're going to use algebraic equivalents that use some easier computations. As you can see here, each one of these contains the term big N times the grand mean squared. Sum of squares error is very ugly. It's very hard to compute, so what we're going to do is take the sum of squares total, subtract the sum of squares blocks, and the sum of squares between to get that term. So I'm going to go ahead and add in some descriptive measures like N, the sum of the x's squared, the mean, the sum of squares, and the variance. So as I mess around here with some symbols, I'll try to find a sigma to put in there. So where's sigma? I'm not finding that sigma. Just delete these e's here. So I want sigma x, or the sum of the x's. I'm going to take all the x's squared and sum them, or sum of the x's squared. I'm going to compute the mean, I'm going to compute the sum of squares, and I'm going to compute variance. I'm going to use the Excel formulas here that we've all come to know and love. The count will give us the number of scores in a sample. Sum will give us the sum of a set of scores. Sum square will give us the sum of the squared scores, all the scores squared. M is the average, the mean, and the arithmetic average. We know that function to be average. The sum of the square deviations of a set of scores from its mean, we use the function div squa. And variance of a sample, we're going to use var.s. Once I get these in here, I'm going to go ahead and select them all and autofill, because if I have them done for one row, I can just block and copy them over to subsequent rows. Dependent sample analysis of variance makes the homogeneity of variance assumption, so I'll just quickly glance at these variances and make sure they're roughly the same. Now to go further, I'm going to now be computing the blocks. I'm going to be computing this BL term, which is the sum of the scores in a block. And then I'm going to square that. So just BL squared. And I'm just going to type in here equals E2 squared. Now I'm doing this because in computing sum of squares blocks, you can see that I need that term. That's why I'm doing it. So here we go. I just auto-filled from there, and now I have the block totals and then the squared block totals. Now I'm going to enter in big N. And I need that for in a few places to calculate some terms. I'm going to also need the grand mean. And then I'm going to compute this term n times the grand mean squared. And as I said earlier, it's in all of the formula for computation. I'm going to determine k, and then sum of squares between, sum of squares total, sum of squares blocks, and then sum of squares error. So for a big N, I'm just going to count all the scores. So I'll use the count function, select my range of scores. I should have 15 of them. The grand mean is just the average of all the scores, so I'm just going to use the average function, select my range, and that will give me the average, the grand mean, or the grand average, or the big average. And I'm just going to multiply n times that grand mean squared to compute this little intermediate term, nmg squared. K is the number of conditions, or groups, treatments. I have 3 of them. That's what K is. So now I'm going to move on to calculating sum of squares between. And what we need to do is we need to take n times each mean squared and sum them. So n times the first mean I square that, and then I'm going to add that to n times the second mean squared plus n of the third group times its mean squared, and then I'm going to subtract nmg squared. That'll give me sum of squares between. Sum of squares blocks, again here, or sum of squares total. And I'm going to sum all of the squared sums, and then I'm going to subtract nmg squared. Sum of squares blocks, I'm going to take the sum of all the block squares, divide by k, and then subtract nmg squared. So this is going to equal sum of all the block squares divided by k, subtract nmg squared. Now to compute sum of squares error, what I'm going to do is just take the sum of squares total, subtract the sum of squares between, and subtract the sum of squares blocks, and that should give me the sum of squares error. Okay. So from here, I'm going to construct an Anova table. I have a source of variability. I have sum of squares. I have the degrees of freedom, mean square, or variance. I have my f and my p-value. So in the dependent sample analysis of variance, we have a source between. There's a between source of variability, there's a block source of variability, and then there's random error. And there's total amount of variability. I indent blocks in error because that is actually equal to sum of squares within. In our partitioning, remember, we've divided sum of squares within into sum of squares blocks in error. And I'm just going to select the appropriate cell reference here to put in my sum of squares terms. Now with degrees of freedom, I'm just going to check to make sure the sum of squares all add up, and they do. They equal the total, so I'm just going to go ahead and delete that. Okay, so to talk about the degrees of freedom, between is the number of groups minus 1, so it's 3 minus 1. The sum of squares total, we'll do that maybe first. That's the sum of the total number of observations minus 1. 15 minus 1 is 14. Blocks is the number of blocks minus 1. So we have 1, 2, 3, 4, 5 blocks minus 1 is 4. And then our error blocks is just going to be, again, computed by taking the degrees of freedom total, subtracting the degrees of freedom blocks and the degrees of freedom between to arrive at, what do we got there? We got 8. Yes. Mean square is just sum of squares divided by degrees of freedom. Sum of squares between is divided by degrees of freedom between will give us mean square between. We calculate mean square blocks. We calculate mean square error. Our f then is our mean square between divided by our mean square error. And our f, our p-value of our f, we can determine with fdis.rt. We need to select the f value and then the appropriate degrees of freedom. In this case, 2, and 8. And we get our p-value.